Walk into 50-degree heat, and your hand starts reaching for the AC remote before you even think about it. Now, take away the remote. Take away the compressor. Take away electricity. Then, step inside an ancient Persian building. It doesn't suddenly feel like winter, but the heat can become much more manageable. And part of that cooling is coming from the building itself. The people inside weren't tougher than you. The architecture was doing some of the work. Some structures were designed to guide airflow. Underground systems help protect water from the direct desert heat. Persian ice houses could even preserve winter ice well into the summer. And the first clue is right above your head. Look at the roof. Look at the roof again. That tower is a Bādgīr, a Persian windcatcher. There's no fan hiding inside it, no motor hub, no cold air being manufactured somewhere above the ceiling. Its job is much simpler. Find moving air and give it a path through the building. Some Bādgīrs had openings facing different directions. Wind hitting one side created pressure that could push air downward, while openings on other sides could help warmer air escape. Warm air rising inside the building could also help pull air through the system. Architectural researcher Susan Roaf describes these towers as part of a long Persian tradition of using the building itself to control ventilation. In plain English, the roof was catching the breeze before the people inside ever felt it. Think of holding a scoop into moving air. The scoop doesn't create wind, it changes where the wind goes. A Bādgīr did that on the scale of a house. And that distinction matters because most of us have learned to think about cooling in the opposite order. A room gets hot, you get uncomfortable. You press a button, then the building gets help. The Persian approach could start much earlier. Before the room became unbearable, the building had already been shaped around questions like, where will the air enter? Where can hot air rise? Where can it escape? Which rooms should get the airflow? The house was part of the cooling system. That's the first answer, but it creates a problem almost immediately because moving air is not the same as making cold air. A desert breeze can still be brutally hot. So if the windcatcher only moves the air, why would the person inside feel that much better? The missing piece is something your own body already understands. Step out of a swimming pool on a hot, dry afternoon. Stay wet, and then let a breeze hit your skin. The air didn't suddenly get 10 degrees colder, but you feel colder. That's evaporation. When liquid water turns into vapor, it needs energy. Some of that energy comes from the heat around the surface, and when dry air keeps moving across the water, evaporation can happen faster. Your skin feels the result immediately. Now imagine using that same physical principle as part of a building. This is where Persian water engineering enters the story. Qanats were gently sloping underground tunnels that carried water over long distances using gravity. Some stretched for kilometers. Vertical shafts along the route allowed workers to dig the tunnels, remove soil, inspect them, and maintain the system. No electric pumps were needed. Gravity kept the water moving. And because much of that water traveled underground, it avoided direct exposure to the desert sun. That matters more than it sounds. The surface can heat up violently during the day. The ground below changes temperature much slower. So water, air, and occupied spaces placed partly underground could escape some of the extreme temperature swings happening above them. In some Persian buildings, windcatchers worked with cooler underground spaces, water or damp surfaces. Air could pass through these cooler zones before reaching the rooms where people lived. Not every house worked exactly the same way. Not every Bādgīr sat above a qanat, but the larger principle stays the same. The Persians were not asking one machine to defeat the desert. They were dividing the problem. Let the roof manage the air, let the ground buffer temperature, let shade reduce solar heating, let underground infrastructure protect the water, let evaporation help when the air is dry enough. They were not creating cold from nothing. They were giving heat easier ways to leave. That's the part modern cooling can make strangely easy to forget. Today, when a room becomes uncomfortable, an air conditioner can actively move heat out of it with incredible precision. That's a huge advantage. But because the machine is so good at correcting the problem afterward, most people no longer need to think much about how the heat entered the building in the first place. Where did the afternoon sun hit? How much heat did the wall absorb? Could the roof have been shaded? Could hot air rise somewhere else? Could people use a cooler, lower level during the hottest part of the day? Most of us only notice the physics when the AC stops working. Ancient builders had much less room to ignore it. And just when wind, water, shade, and earth seem to explain the whole mystery, Persian engineering gives us a harder problem. Ice. Take one ice cube out of your freezer, put it on a plate in summer, do nothing. You can literally watch heat win. The corners soften, water appears underneath, the cube gets smaller, eventually it disappears. Now scale that up. Imagine trying to keep a large supply of ice available through a desert summer with no compressor constantly pulling heat away. That was the problem solved by the yakhchal, the Persian ice house. And this is where the popular version of the story needs a correction. The Persians were not routinely taking liquid water during a 50 degrees Celsius summer afternoon and somehow freezing it on command. In documented systems, ice could be produced during cold enough winter conditions, sometimes in shallow outdoor basins, or brought in from colder regions. Then the real challenge began. How do you stop that cold from disappearing for months? Yakhchals could use thick earthen walls, deep storage pits, shade, small controlled openings, large amounts of thermal mass, and the steadier temperatures below ground. The point was not to create cold every second. It was to slow down the arrival of heat. Think of two identical ice cubes. Leave one on a sun-baked stone, the other in a thick insulated cooler. Neither cooler manufactures cold, but one receives heat much slower. Now replace the plastic cooler with earth, depth, shade, thick walls, carefully controlled airflow, and seasonal timing. That's what makes the yakhchal so interesting. The smartest part may not have been making the ice. It was making time part of the design. Cold was available in winter. Capture it, store it, slow the heat, use it later. They didn't need summer to become winter. They needed winter's cold to survive into summer. And these systems had real limits. They depended on the right climate. Evaporation works best in dry air. Qanats required water, excavation, maintenance, and enormous practical knowledge. Ice storage depended on winter cold or access to ice from colder places. Modern air conditioning is far more controllable and can work in situations where passive cooling alone would not be enough. So this is not a story about ancient technology being better. It's about different constraints producing different solutions. Ancient Persian builders could not turn a thermostat and demand comfort from a room, so they worked earlier in the chain. Wind above the roof, water below the ground, shade before sunlight reached the wall. Thick materials slowing the heat, cold seasons helping hot seasons months later. And once you see all of that, the mud brick building stops looking passive. It starts looking like a machine made out of architecture. Passive is not the same as primitive. No electricity is not the same as no technology. Modern machines made temperature easier to command. Ancient Persian buildings made the physics harder to ignore. If this changed which of those two words feels more accurate, write just one. Passive or primitive?